Hello.
So welcome you all to ICNTDM contributory session. It's a matter of great honor to welcome Dr. Indulal Ji to chair the contributory sessions in ICNTDM 2020. Dr. Indulal Ji is an associate professor in mathematics at St. Aloysius College, Alappuzha. On behalf of ICNTDM, I welcome you, sir, to chair the sessions.
Okay, thank you very much for the nice introduction, and I extend my thanks to the organizers for giving me a chance to chair this contributed session. And I think almost all participants have been joined the meeting. And I think we can begin. I request all of the participants to take a note on this matter, that we have a very strict time-bound schedule, and we have 15 minutes for presentation, and in this 13 minutes are for presentation and 2 minutes for a fruitful discussion. So I think we can begin the contributed session with the first paper on the pendant domination in grid graphs. Am I audible?
Yes, yes.
Yes, okay. So we begin with the first talk on pendant domination in grid graphs. As all of you know, that domination is a very recently gained momentum in research area. And here the speaker speaks on dominating set which contain at least one pendant vertex. The induced subgraph of S contains at least one pendant vertex, and they named it as pendant domination. And they discussed the pendant domination number of some grid graphs. So may I know who is presenting the article? Who is giving the talk? See, this is a joint work of Purushottama, Puttasamy, and Nayaga. May I know who is presenting?
Abstract number 18, right, sir?
Yes, yes, abstract number 18. See, I'm calling you in this order. See, 18. See, let me give you the order of presentation first. See, first abstract number 18, then abstract number 40, 58, 67, 69, 70, 71, 75, and 83. So we begin with abstract number 18, pendant domination in grid graphs. So may I know who is presenting? So am I audible?
Yes, sir. You may go for the next one.
Okay, so C18 is absent. So I call upon C14 on the uniform number of graphs and other graph invariants. On uniform number of graphs and other graph invariants by Elakya, Mohan Kumar, and Kumar Abhishek. So who is presenting? It seems that C40 is also absent as of now. So let us go for 58.
Yes, sir. Am I audible?
Properties of semi-splitting block graphs of graphs.
Yes, sir. I'm myself
Okay.
Niveda.
Niveda.
Yes, sir.
Okay. So over to Niveda Bhaskar for the presentation.
Thank you, sir. Is my screen visible, sir? Hello?
Yes,
sir, is my screen visible now?
Yes, one second.
Okay.
Yes. Properties of, as I can see.
Okay, sir. Thank you. So good afternoon, everyone. Myself, Niveta. I'm a research scholar at Christ University. So today my topic is on semi-split properties of semi-splitting block graph of a graph. It is basically a derived graph. So we'll start with, this is a joint work of Tabitha Rajshekhar and Dr. Mukti Acharya. And starting with preliminaries, some basic definition, which will be useful for our topic. So to study on semi-splitting block graph, we have to start with the splitting graph of a graph. This concept was introduced by E. Sambat Kumar and H.P. Valika. The definition is, for a given graph G, the splitting graph, which is denoted by S of G, is a graph obtained by taking a copy of G. And for each vertex of a graph, a new vertex is added and it is made adjacent to all the vertices adjacent to V. So for every vertex in a graph G, a new vertex is basically added and it is made adjacent to all the neighborhood of that vertex. So in this paper, they have studied on the structural properties of splitting graph, and they also characterized the graph which was splitting graph. So this was introduced in late 90s, and there are a couple of papers the authors have worked on this concept. So motivated by this concept and the definition of block graph, Professor Kulli have initiated the concept of semi-splitting block graph of a graph. So this is splitting graph is a subgraph of this semi-splitting block graph. So it is denoted by SB of G. So to explain this definition, I'll explain this with an example. So it will be easy for understanding. So given a graph G, as I said, SB of G, that is I'm denoting the semi-splitting block graph of a graph as SB of G. So SB of G is S of G is a subgraph of SB of G. So basically what we do is a splitting graph. For each vertex, we take a new vertex and we made it adjacent to all the vertices neighborhood of V1. Suppose for the vertex V1, a new vertex V1 dash is introduced and it is made adjacent to the neighborhood of V1. So the neighborhood of V1 here is V2, V3 and V4. So it is made adjacent to V2, V3, V4. Similarly, for all vertices in G, a new vertex is introduced and it is made adjacent to its neighborhood. And this is one part of the definition. Another part is based on the blocks of the graph. So basically, what is a block of a graph? Block of a graph is a maximum connected subgraph which has no cut vertex. So in this graph, in our example, we have two blocks. This is the cut vertex. So like, can you see, this is V1, V2, V3 is one block and V1, V4 is another block. So we have two blocks in this graph. So for each block in a graph, a new vertex is introduced, say small b1, and it is made adjacent to all the vertices that belongs to that block. So the block b1 has two vertices, v1, v4. So in SB of G, a new vertex small b1 is introduced and it is made adjacent to vertices of b1, that is v1, v4. Similarly, a new vertex b2 is introduced and it is made adjacent to all the vertices that belongs to that block, capital B2 here. I hope it's clear with the definition. And so we'll start with some of the observations that we can get it from the definition directly. Starting with when we try to get the semi-splitting block graph of K1 is disconnected, obviously. To talk about the connectedness, next theorem is on connectedness. So SB of G, that is semi-splitting block graph of a graph, is connected if and only if G is connected for n greater than 1. So when n is equal to 1, that is G is K1, it is disconnected. And the next theorem is on the degree of vertices of SB of G. So as in the definition, we know the vertex set is partitioned into three subsets, that is V of G, V1 of G, and B of G. So we are going to tell the degrees of the vertices that belongs to V of G, that belongs to V1 of G, and B of G. So this is, first we we say that the degree of the vertices that belongs to the set V1 of G. So for each Ui belongs to V1 of G, the degree of Ui in SB of G is equal to the degree of Vi, because for every vertex, we add a new vertex and it is made adjacent to the vertices adjacent to V1. So obviously degree of Ui, that is V1 dash, is equal to the degree of V1 in G. So it's direct from the definition. When we see the definition, it's very clear. From the definition, we can conclude this. And the next is for each BL belongs to B of G, that is the blocks. Based on the blocks, we introduce few vertices, small b1, b2. For that kind of blocks, for that kind of vertices, the degree of BL is equal to the cardinality of the BL, the cardinality of the block. Here, the cardinality of B1 is 2. So degree of the small b1 is 2. And the cardinality of B2 is 3. And the degree of B2 is 3. And the next remaining set is V of G. The vertices that belongs to the set V of G has the degree twice the degree of Vi plus S, where S is the number of blocks that Vi belongs to. And the next, suppose the vertex is a non-cut vertex, then the degree of SB of G of Vm, that is a vertex which is not a cut vertex, is equal to twice the degree of Vm in G plus 1. Because when a graph is when a vertex is not a cut vertex, then it is exactly adjacent to only one block vertex. So obviously S is equal to 1 here. So when G is a block, so when a graph is said to be blocked, when the graph has no cut vertices. So when the graph has no cut vertices, when we look back to the definition of semi-splitting block graph, we can say there exists exactly one block vertex, only one vertex. There exists only one block anyway. So there exists only one block vertex called B1. So obviously the degree of the B1 will be the order of the given graph. Order of the given graph here is n, it's equal to n. And since all the vertices in the graph is non-cut vertex, from this we can claim the degree of the vertices Vi that belongs to V of G is twice the degree of Vi plus 1. And the next theorem is on the cardinality of the vertex set and edge set of SB of G. So for a given, for a connected PQ graph, the cardinality of vertex set of SB of G is equal to twice 2p plus k, where k is the number of blocks in the graph. And the cardinality of edge set is equal to 3 times the edges plus summation of degrees of BL, where L lies from 1 to k. And the next is more on the structural properties of SB of G. This theorem states that for any graph G of order n greater than 1 with k blocks in SB of G, each BL is adjacent to at least one open neighborhood of a vertex in BL, contributing to at least one C3. If and only if each component of G has at least 2 vertices. We insist on this condition because SB of K1 is disconnected. So it increases the number of components of SB of G. So this is why we say this later part is because each component should have at least 2 vertices, because that when one of the component is K1, then the number of components of SB of G increases. So this is very important when we talk about the front part. So based on this, we can say, so from this, what we can say is like every SB of G has C3 for each BL. So we know the characterization of for any graph to be bipartite. Any graph said to be bipartite if and only if it has no odd cycle. But from the theorem, we know that every SB of G, when this condition satisfied, when n greater than 1, has C3. C3 is odd cycle. So obviously, SB of G, when given graph is of order n greater than 1, is never going to be bipartite. And then we know that the smallest cycle of any graph can be 3. So, and we know that all the graphs has C3, all the SB of G has C3. So the girth of SB of G is equal to 3, where girth is the length of the shortest cycle in a graph. So these are the corollaries that we can conclude from this theorem. Moving on to the next is on the unicyclic characterization of unicyclicness of SB of G. For any graph, for any connected graph of order n, SB of G is unicyclic if and only if G is isomorphic to P2. Next, from this we can, when we talk about the disconnected graph, for any disconnected graph of order n, SB of G is unicyclic if and only if exactly one component is P2, others are K1. And this is the more generalized result on number of partites of a graph and its semi-splitting SB of G. So for any graph which has T partite of order n, then SB of G has T plus 1 partite. Next is on chromatic number of a graph of SB of G. For any graph G, the chromatic number of SB of G is exactly equal to the chromatic number of the original graph plus 1. Next, for any graph of order n, SB of G is never Eulerian. This can be directly, it seems to be a very a generalized one, but it can be directly concluded from the degrees of vertices from this from the theorem 3, we can directly conclude it, because we know that every graph of n, at least for an order of n, at least 3, there exists a non-cut vertex. We know the degree of a non-cut vertex is twice the degree of the cut vertex plus 1. So this is going to be odd. So anyway, we know that the characterization of Eulerian is a graph is said to be Eulerian if and only if every vertex are of even degree. But from this we can conclude there exists a non-cut vertex in the graph of order at least 3. And also it is odd. It's directly from the definition, from the degree of the vertex. So obviously no SB of G can be Eulerian. Next is on the vertex connectivity of SB of G. For any connected graph of order n greater than or equal to 2, the vertex connectivity of SB of G is equal to the del of G, that is a minimum degree of the graph when G is a block, 1 when G has a pendant edge, 2 otherwise. Next theorem is on edge connectivity of SB of G. For any connected graph of order n greater than or equal to 2, edge connectivity of SB of G is equal to 1 when G has a pendant edge, 2 when G has a bridge and no pendant edge. Otherwise, the value is del of SB of G.
Niveda, you have 1 minute, 1 minute more.
Sure, sir, sure. And the next theorem is on the vertex covering number and the vertex independence number. For any graph of G of order n greater than of order n with no isolated vertices, alpha naught of SB of G is equal to 1 and the vertex independent number is equal to n plus k, where k is the number of blocks in G. And the next is on for any graph G of order n with no isolated vertices, vertex alpha 1 of SB of G is equal to twice the alpha 1 of G plus k, and beta 1, that is matching number, beta 1 of SB of G is equal to twice the beta number of the given graph G. This, thank you. And these are the references for my topic. Thank you. Yes.
Okay. Any questions from the participants? Any questions? Okay, Niveda, I have a few questions.
Yes, sir.
See, in page 6, you said that the semi-splitting graph of K1 is disconnected.
Yes, sir.
So can you explain why it is so?
So, according to the definition, so K1 is a single vertex.
Yes.
So for a vertex, we'll take another vertex, say V1 dash. So it is disconnected. We have V1 and V1 dash, and V1 is a block. We consider V1 as a block.
So even though this K1 has no adjacent vertices, you will take one more vertex.
Yes, sir.
Okay.
So that will be SB of K1 is
fine.
Okay.
Why you choose this name semi-splitting block graph instead of some splitting block graph?
Yes, sir, because the definition of block graph is slightly different from what we are using here. The definition of block graph is they won't take the original graph. The definition of block graph.
No. When you add splitting, that is different. Splitting block graph.
Yeah, it could have been a splitting block graph of a graph, but we didn't take the exact definition of block graph. That's why we are just taking a partial definition of block graph.
Okay.
That's why it becomes semi.
Okay. And one more question. See, in one of your slides, you showed that semi-splitting graph of P2 is unicyclic. Yes. Semi-splitting block graph of P2 is unicyclic. And in addition to that, this is self-complementary also. The semi-splitting graph of P2 is the A graph, which is self-complementary.
Okay.
Okay. Self-complementary on 5 vertices. Did you do anything on that line, that a semi-splitting graph or some graph is self-complementary if and only if?
No,
Or
sir, we haven't
if
worked.
if there are no other graphs, then you can conclude that SPG is self-complementary if and only if G is P2.
Sure,
I
sir.
think you
Thank you
can
for the
add
point. Yeah,
that also if
I'll look
possible.
into it. Okay, sir.
Okay, and as there are no questions from the participants, let us congratulate Niveda for the nice presentation.
Thank you, sir.
Okay. Next, abstract number 67 on the intersection ideal graph of semi-groups by Jitendra Kumar and Barkha.
Yes, am I audible?
Yes, yes. May I know who is presenting?
I'm Jitendra Kumar.
Okay, okay. Now over to Jitendra.
Yeah, let me share my screen. Yeah. Okay, so good afternoon, all of you. So this is basically, we have studied this intersection ideal graph of semigroup. So why this graph is basically we have chosen, the motivation is behind this is that we have seen nowadays basically various graphs are constructed through the algebraic structure, and main motivation is that there are various works basically related to this graph over the ring structure, over the module structure, over the group structure. So that's what we become motivated, since we are working in the semi-group theory. So we thought of to construct this graph and see what kind of interaction between the graph theoretic property and the algebraic property of semi-group is there. So even we have find out very interesting results. And of course, this is basically joint work with my PhD student. Okay, so let me start with a very basic definition. I hope all of you are familiar with this definition. So semigroup is, as we know, this is non-empty set with associative binary operation. An interesting example of semigroup, basically this is an analog version of the symmetry group in group theory as we used to see. And full transformation semigroup is also basically an important concept in case of semigroup theory. And some of you might be familiar with that contribution in the study of full transformation semigroup. And this is nothing but basically a non-empty set. And if I collect all the mappings over this set X, so this forms a semigroup with respect to composition of mappings. Another interesting example of this semigroup is basically Rees matrix semigroup. So this construction was done by Rees, and the underlying set basically you can see this is I cross G cross lambda, capital lambda. G is in between group structure, and I and lambda are basically index set. And in between you see P is there in the notation. So P is this kernel of lambda cross kernel of I matrix, where the entries of this P is nothing but G union 0. And this matrix P is considered as a regular matrix. Regular matrix basically in the sense that in the no row or column of P consists entirely of 0. Means in each row and each column there are non-zero entries. And binary operation is given between the elements of our this semigroup is I a lambda j b mu. If I just do the product, so this gives I and a p lambda j b mu, right? If lambda jth entry of our regular matrix is non-zero, otherwise it is 0. And if I just do the product with 0, it gives me 0 always. Okay. An interesting thing is there in between this G, one can take semigroup structure also. And if I take G to be trivial group structure, and or in another way, let me just explain first. If I take kernel T of lambda and kernel T of I to be same, and this P is if I construct an INT matrix. So again, in semigroup theory, this gives an interesting class. Basically, this is completely zero simple inverse semigroup if my P becomes INT matrix. And this semigroup we used to say Brandt semigroup. In particular, if size of I is finite, say n, and G, if I take it to be trivial, then it is called a Brandt semigroup Bn. Again, this example is also very much useful in case of semigroup theory. And most of the time, basically, this example is also called as basically counter example. Most of the time, it works as a counter example whenever we see something in the semigroup theory. Okay. Okay, let me come to the my basic definition of the graph. So intersection ideal graph. So you can see in the bottom, basically the motivation to construct this graph is basically these two papers by I. Chakrabarty in 2009. It published in Discrete Math, and S. Akbari et al. in 2013, Journal of Algebra and Application, they have basically constructed this intersection ideal graph over the ring structure, and further intersection ideal graph over modules and another structure is also results was developed on that, and basically very nice connection was given. So if I know some graph theoretic property, what I can say about the algebraic structure, and if I know, if I just implement something over the algebraic structure, how this graph behaves. Okay, so let me go back to my basic definition. So intersection graph of a semigroup S is just our simple undirected graph. So here vertices we have taken non-trivial left ideals, and adjacency will be there in between those two vertices if their intersection is non-trivial. Okay. So these are the example of graph. If I just taken my semigroup which is generated by A under this relation A6 equals to A9. So this gives me this graph. So all the ideals are listed here. Another example like full transformation semigroup, if I take X to be my two element set 1, 2. So this is graph of the intersection ideal graph. Okay, so this is again you can see interesting graph. So this is basically over the brand semigroup B4. So basically it has 4 left ideals. And interesting news in basically in the semigroup theory, what we have, if I just take 2 ideals and if I take their union, so it becomes an basically again an ideal. Whereas this facility we don't have for the like in case of ring structure, we know that union of 2 ideal may not be ideal, but in case of semigroup we have this liberty, and this gives very interesting results. So because of that union of 2 ideal becomes an ideal, we are able to identify basically all the vertices of this completely zero simple semigroups, and B4 is one candidate of that class. So this is the example of intersection graph of B4. Okay, so let me show you that what kind of interesting results we have obtained. So first we have studied about the connectedness of this graph. So intersection ideal graph. So this is basically disconnected if and only if S contains at least 2 minimal left ideals, and every non-trivial left ideal of S is minimal as well as maximal. So immediate corollary of this, you can observe that gamma S is disconnected. Whenever it is disconnected, basically it is a null graph. The graph gamma S is disconnected if and only if S is the union of exactly 2 minimal left ideals. So basically this gives a complete classification when our semigroup will become connected. And when our semigroup is connected, we observe that diameter is coming at most 2. Further, we have classified that when my diameter is 2, what I can say about the semigroup structure. And this result is when semigroup has n minimal left ideal, then gamma S is complete if and only if n equals to 1. Means it should have only one minimal left ideal. And this is again a classification when our diameter of our given graph is 2. If and only if S has at least 2 minimal left ideals. Then further we have computed the girth of this graph, girth, which we used to say if gamma contains a cycle, then girth becomes 3. So another classification when our this intersection graph is star free graph, tree or bipartite, then basically you can see here that this semigroup should have exactly 3 left ideals. One is I1, another one is I2. This I12 is notation for basically I1 union I2. This I want to make it clear, this notation. I12 means I1 union I2, which is union of 2 minimal left ideal. As I have already pointed out, this becomes again an ideal in case of semigroup. So this is the classification for intersection graph to become star graph, tree and bipartite. Further, we have find out the independence number of our graph. So if S is a semigroup which has n minimal left ideal, then its independence number is n. Further, perfectness is observed for the graph gamma S, means intersection ideal graph of the semigroups. So this is perfect if if it is perfect, then min S means number of minimal left ideals of S is at most 4. And if S be the union of n minimal left ideal, then gamma S is perfect if and only if n is at most 4. So basically when S is union of n minimal left ideal, then we have done basically complete classification for the perfectness. If in general we are able to say only one side result. S is union of n minimal left ideal, basically it also covers a bigger class of semigroup. Basically all completely zero simple inverse semigroup is part of this class when S is union of n minimal left ideals. Okay, this notation I have already introduced to you. So I suffix I1, I2, Ik means union of these minimal left ideals. So first, in order to find out now chromatic number of this graph, first we have find out the chromatic number of our that semi group, which is union of n minimal left ideal. Means one can also observe that all completely zero simple inverse semi group is basically part of this lemma. If S is this one, then chromatic number of this is 2n minus 1 minus 1. Okay. Then now in order to find out, suppose this chromatic number for arbitrary semi group. So then we have proceed and we have first constructed these three sets, x1, x2 and x3. x3 is basically all those vertices which is other than x1 and x2. Okay. So, before to find out that chromatic number, of course, we could not find out chromatic number of arbitrary semigroup, but we have given this upper bound. And in order to get this result, we have defined this relation on the set X3, which I have shown just earlier. So two elements will be related if and only if this min j, tilde min j and tilde min k is basically, they contain same minimal left ideals. So that is the notation for min j tilde, means the ideals which contains this j. So this result basically gives an upper bounds of our intersection graph of arbitrary semigroup. Okay, and still basically this work is in progress so far, and we are working on like automorphism group and metric dimension, all kind of result we are still working on. But this is again very interesting result which we have observed, which gives an upper bound of the chromatic number of this graph. And these are the basic references. You can see intersection ideal graph over ring is there. Second, basically related to module. Third one again is same graph over the rings. And for semigroup theory part, we have focused on this book, Clifford and Preston. And you can see basically second and third, basically intersection graph of the group structure and semigroup structure. And these are the basically same papers in that same lineup. And this last one is basically intersection graph of a module. Okay, so that's all from my side. Further, if you have any query or suggestion, you can give. So that's all from my side.
So may I ask question?
Yeah, yes, sir, please.
Myself is Vinayak Joshi. There is a very nice connection between the zero divisor graphs.
Yes, sir. I have seen you. There are you have worked on the perfectness also, right? Over the zero divisor graph.
Yes. Connectedness, disconnectedness also I think follows from our results, because
of
there
this
is
graph.
one more paper which talks about the connected and disconnectedness of complement of zero divisor graphs.
Complement,
and
okay.
complements of zero divisor graphs of ordered sets and the intersection graphs of semi-groups, ideals of semi-groups. They have the connection. So from that result also, your result, I think you can get that result immediately, because we have proved that if we have two items there, then that is not possible. So
okay, sir, just may I interrupt you? I think this complement of zero divisor graph, like paper you are in this Australian Math Society, right?
No. That is first one. The second one is with Professor Lagrange.
Okay.
So just go through there are three papers with me and my colleague Sarika Devare and John Lagrange. Three papers are there. They give the applications these two intersection graphs of intersection closed family. So intersection closed family. So naturally, the ideals of semigroups are intersection closed family. So naturally, these results can be applied. So a suggestion is that just go through that paper. Some of the results may be deduced from that papers.
Okay. It would be better. It would be very interesting. I think if we can see the connection between these two structures.
Yeah. There are three papers. If you are interested, you can send me a mail. I can send it to you.
Yeah, sure. I will send you a mail. I hope you can provide me the those relevant references.
Yes, definitely.
Okay. Yeah. Thank you to point out. Yeah.
From my side. Okay.
So only connectedness part you are saying that can
connected and Eulerian, Hamiltonian basic properties we did.
Okay.
perfectness.
But Eulerian
which we call-
Hamiltonian, we have not worked out for that kind, because
Yeah,
we know
so
we
that-
don't know the complete vertices here. Basically, that is the main
Okay.
thing. For completely zero simple semigroups, we know all the vertices.
Okay.
Oh,
So
so that's
you
what
can
we
have a
have.
look, and you can have a look, and we can discuss also later on also.
Yeah, sure. Yeah,
Yeah,
yes, sir.
just
It would be my
for
pleasure
your
if I could
yes.
collaborate in
Yes.
that way. Yeah. Thank you,
Yes,
sir.
yes.
Yeah. Thank you
Okay,
very
thank
much. Yeah. Yeah. Any other comments or suggestion?
Any further questions from participants? Okay, let me ask you one question, Jitendra.
Yeah, sure.
Okay, this gamma S, the intersection graph of this semi-group ideal
Yes, yes.
group is of diameter less than or equal to 2.
Yes, sir.
Is it an advantage or a disadvantage when we can consider gamma S? So because gamma S is then a very restricted class of graphs with a diameter less than or equal to 2.
Yeah, in the sense of graphs, if you see, yeah, that class is basically, of course, restricted, because basically if I take any two vertices, we are getting a path just by joining with one more vertex in between. Yeah.
Okay.
Yeah. But
So
here in the semigroup side, basically you can see this third one is basically, if I have this kind of diameter, we could classify our semigroups.
Okay. Another one is, have you studied anything along the lines of caudality of gamma S?
No, sir. So far that we are basically working on like automorphism group and metric dimension.
Okay.
Thanks
Because
for your
that-
suggestion. I think we can see in that way also, but that is, I think, topological side, right, of the graphs.
Yes.
Yeah.
And last,
yes, sir.
you stated that girth of gamma S is 3, I think.
Yes, sir.
Any study on lines on circumference of gamma S have been carried out?
Sorry, which study, sir?
Circumference, the length of the greatest, longest cycle.
Okay. Yeah, I understand your point. But so far we have not made any attempt in that direction, because this work is almost we have just started.
Anyway, the circumference cannot be greater than or equal to 6. It will be less than or equal to 5, because the diameter is 2, and if the circumference is 6, then it will be of diameter 3 at least.
Okay.
So I think you can characterize graphs if possible with the circumference 4 and 5.
Yeah. Okay.
Possible. Okay. Thank you for the nice presentation.
Yeah.
And
okay. Thank you to
thank you.
all of you. And in particular, thanks to Vinayak sir. I will contact you through mail. Okay. Thank you, sir.
And the next presenter, the next paper is on the abstract number 69. Pavitra?
Sir, am I audible?
Yeah, okay. See, Pavitra will present on coupon coloring of Cayley graphs. In fact, coloring of graphs is a very fascinating research area for all researchers, starting from the four-color conjecture, four-color problem proposed by Francis Guthrie in the 19th centuries. So anyway, the speakers speak on a new coloring called K coupon coloring. And over to Pavitra.
Thank you, sir. Good afternoon, all. And myself, Pavitra R. And this is a joint work together with Dr. T. Raji. Our topic is on coupon coloring of Cayley graphs. First of all, I would like to thank the organizers of ICNTDM for giving me this opportunity. We'll start. The concept of coupon coloring number was introduced by Bobson, Jeong-Han Kim, Michael Tite, and Jacques Verstraete in 2014. Coupon coloring is an improper coloring, vertex coloring. We will see the definition. Let G be a graph without isolated vertices. A K coupon coloring of G is an assignment of colors from the set 1, 2, 3, etc. K to the vertices of G such that the neighborhood of every vertex of G contains vertices of all colors from the set 1, 2, 3, etc. K. That is, any vertex must be adjacent to the vertices with all colors from the set 1, 2, 3, etc. K. So from the definition itself is clear that the coupon coloring is an improper coloring. That is, distinct vertices may have the same color. The maximum K for which a K coupon coloring exists is called the coupon coloring number of G, and it is denoted by chi C of G. Clearly, chi C of G is less than or equal to delta of G, the minimum degree. Note that in a coupon coloring, each color must appear at least twice. The coupon coloring is closely related to total domination. The coupon coloring number is also referred as the total domatic number. We will see the definition of dominating set. Let G equal to B, E be a graph. D subset of V is a dominating set if every vertex in B minus D is adjacent to at least one vertex in D. Let G be a graph without isolated vertices, then D dash subset of V is a total dominating set if every vertex of G is adjacent to at least one vertex in D dash. So from the definition, it is clear that every total dominating set is a dominating set, but the converse need not be true. The total domatic number is the maximum number of disjoint total dominating sets. So we have already said that the coupon coloring number is also referred as the total domatic number. Suppose that C is a coupon coloring of G, then consider the set of vertices with color 1. Then this color class must be a total dominating set. And we are looking for maximum such K. So the total domatic number and coupon coloring number is one and the same. Yongtang-Shi et al. Determined the coupon coloring number of complete graphs, complete K-partite graphs, wheels, and some basic graphs. And we will use these theorems. Let G be a complete graph, then the coupon coloring number of complete graph is the floor function of n by 2. And for complete bipartite graph, the coupon coloring number is like this. Now we will move to the definition of Cayley graphs that we are studying in this paper. Let G be a group and let C be the subset of G that is closed under taking inverses and does not contain the identity. Then the Cayley graph of this group G is a graph with vertex at G and edges at set of all GH such that HG inverse belongs to C. And the Cayley graph with group Zn is called the circulant graph of order n, and C is called the connection set. Now, the Cayley graph of a group was introduced in 1876, but Cayley graph of commutative rings was introduced by Futz in 2005, and we will see the definition. Let R be a commutative ring with unity, then the Cayley graph of R with respect to the zero divisor is the graph Cayley graph of R plus. That is the group we are taking is the additive group of the commutative ring, and the connection set is non-zero zero divisors. We will denote this by script CAY of R, and we will read as Cayley graph of R. This is the Cayley graph whose vertices are all elements of the additive group R plus, and in which two distinct vertices X and Y are adjoined by an edge if and only if X minus Y belongs to non-zero zero divisor set of R. Alepur and Akbari studied the basic properties of Cayley graphs of commutative ring with respect to its zero divisors. These are some works done by them. Cayley graph of R has no edge if and only if R is an integral domain, and if Rm is an Artinian local ring, then the Cayley graph of R is a disjoint union of this number of copies of complete graphs. And Cayley graph of R cannot be a complete graph. Finally, Cayley graph of R is a regular graph of degree, cardinality of zero divisor set of R minus 1 with isomorphic components. In this paper, we have studied the coupon coloring number of Cayley graphs of two commutative rings Zn. Zn means the integers with modulo n, and the Cartesian product of Zn, that is Zn cross Zn. Cayley graph of R has, we have already seen that Cayley graph of R has no edge if and only if R is an integral domain. So we consider Zn with n composite. Our first observation is, if set of Zn is an ideal of Zn, then coupon coloring number of Cayley graph of Zn is the floor function of cardinality of zero divisor set of Zn divided by 2. The proof is really easy using the previous results because set of Zn is the maximal ideal of Zn, and we get the result. The next result is, suppose that set of Zn is not an ideal of Zn, then we get a lower bound which is sharp. That is coupon coloring number of Cayley graph of Zn is greater than or equal to n by p, where p is the least prime divisor of n. And this is the outline of proof. In this proof, we have done is that we partition the elements of Zn and give each partite set with the same color. Then it is easy to verify that this is a coupon coloring. and we said that the above lower bound is sharp when n is even. Since n is even, 2 is the smallest prime divisor of n. So by the previous result, we can say that it is greater than or equal to n by 2. Each color in a coupon coloring must appear at least twice. So there can be at most floor function of n by 2 colors in a coupon coloring of Cayley graph of Zn. Therefore, it is equal to n by 2. Now we will see the coupon coloring of a Cayley graph of Zn cross Zn. First of all, if R1 and R2 are two finite commutative rings, regular elements of R1 cross R2 means that the R minus zero divisor set of R. That is simply the units in the commutative ring. Then regular graph of regular elements of R1 cross R2 is equal to regular element of R1 cross regular element of R2. So AB belongs to the zero divisor set of R1 cross R2 if and only if either A belongs to zero divisor set of R1 or B belongs to zero divisor set of R2. Therefore, Cayley graph of in Cayley graph of Zn cross Zn, xy is adjacent to AB if and only if either x minus A belongs to set of Zn or y minus B belongs to set of Zn. Since we are looking for the degree of Cayley graph of Zn cross Zn, and since cardinality of set of Zn cross Zn is Nm minus phi of n phi of m, where phi is Euler phi function, Cayley graph is a regular graph with degree Nm minus phi of n phi of m minus 1. And this is another result. Cayley graph of Zn cross Zm is a connected graph with diameter 2. This is really easy to prove. And this lemma characterizes the vertices of xy, the exact vertices of that is Nm minus phi of n phi of m minus 1 vertices are there, and we list this. The next result is the coupon coloring number of Cayley graph of Zn cross Zm greater than or equal to Nm by p. That is, we got a lower bound for the Cayley graph of Zn cross Zm, where p is the minimum of least prime divisors of n. The proof technique was the same. First, we partition the elements of Zn cross Zm with Nm by p partite sets, and we give each partite set with a specific color. Then it is easy to verify that this is a coupon color. And the above lower bound is also sharp if n or m is even. And if n or m is even, then the coupon coloring number of Cayley graph of Zn cross Zm is Nm by 2. Our main result is to find the exact coupon coloring number of Zn cross Zm, but we have so many restrictions because finding a lower bound is comparatively easy, because we have to specify there is a we need only to show that there is a k coupon coloring exists, but to show that it is there is an upper bound, it is something really hard, because we have to show that there is no, if we have to say that there is a upper bound k, then we have to show that there exists no k coupon coloring greater than or equal to, there is no k coupon coloring for greater than or equal to that number. So it is really hard. For this, we first prove this lemma. Suppose that p and q are prime numbers with p less than or equal to q, then a dominating set of Cayley graph of Zp cross Zq contains at least p vertices. Using this lemma, if p less than or equal to q, we have already seen that there is a lower bound, and chi-c of Cayley graph of Zp cross Zq is greater than or equal to pq by p, that is equal to q. From the above lemma, we can say that dominating set of Cayley graph of Zp cross Zq contains at least p vertices. So any total dominating set, we have already said that any total dominating set is a dominating set. So any total dominating set must also contain at least p vertices. Hence, there can be at most q disjoint total dominating sets. Actually, coupon coloring number was also referred as the total domatic number. So the coupon coloring number of Zp cross Zq we can say that it's less than or equal to q. So we get the result. Suppose p and q are prime numbers, then chi-c of Cayley graph of Zp cross Zq is equal to maximum of p comma q. Finally, we have found some coupon coloring on some circular graphs, two circular graphs actually. The first one is with connection set 1, -1 and a equal to -a, that the additive inverse of a is same. same as the element. This is a 3 regular graph, and we have found that the chi-c of Cayley graph of Z and C is exactly like this. And the second one is with connection set 1, -1, 2, -2. And in 2 cases, we proved that it is the coupon coloring number is exactly 3 if n is congruent to 0 mode 6 or n is congruent to 0 mode 7. And these are the references. Thank you.
Okay, any questions from participants?
Please give me the definition of your color. That is
Definition of the coloring.
what you call it, coupon coloring, no? Because somewhere you have told coupon coloring is not a proper coloring. Is it true? Am I right?
It is an improper coloring because
Improper coloring, you mean that there may be adjacent verses receiving the same color.
yes, distinct vertices may have same color. In proper coloring, we will say proper coloring, distinct vertices must have distinct color. But here, this is not the case because see the definition.
No. In usual coloring, adjacent vertices will receive different colors.
Sorry, sir. Adjacent vertices receive
have different colors, but when you say it is improper, that
same color can be possible in this coupon coloring.
In coupon coloring, then
ma'am, please see the definition. A coupon coloring of a graph G is an assignment of colors from the set 1, 2, 3, etc. K to the vertices of G such that neighborhood of every vertex of G contains vertices of all colors from K. Suppose that we are considering a vertex with color 1, then that vertex should adjacent to all vertices of colors with vertices of colors with 1, 2, 3, etc. K. So the one colored vertex must be adjacent to a one colored vertex. So that is why it is an improper color.
You want to maximize the number of colors, or you want to minimize the edges adjacent verses with the same color?
Ma'am, I didn't understand. Could you please?
Want to maximize number of colors.
Yes.
Because according to me, what I have understand, if it is an improper coloring, Mama, one color is sufficient. You are given condition.
One coupon coloring is always there, but we have to maximize the K coupon K.
But maximum K. You want to maximum K for which that happens.
Yeah.
Does it has any? Why you are telling that once I take a vertex, I label it to color 1. Okay. And then all other colors will be distinct. So why should I label in the neighborhood color with one color vertex with one color only? I can label with 2, 3, 4. So does it has any connection with the rainbow coloring?
No, ma'am. It is actually connected with the total dominating set. I have already said that a total domination is different from domination. It is a stronger condition. That is a total dominating set. If every vertex of G must be adjacent to at least one vertex of G. That is, if D dash is a total dominating set, then any vertex of D dash must also have a neighbor in D dash itself. So that is why we are getting an improper coloring.
In your definition, graph may not have a isolate vertex. Should not have isolate vertex.
No. The graph without isolated vertex.
Isolate vertex.
Yeah.
Without Okay, no problem. It's okay. Thank you.
Thank you.
Okay, any further questions? Any further questions? No. So okay, congratulations, Pavitra.
Thank you, sir. Thank you.
The next speaker abstract is the next number is 70. Vaishnavi.
Yes, sir.
Okay. Vaishnavi speaks on fold thickness of graphs. So you have 30 minutes for presentation and 2 minutes for discussion.
Video open.
Over to Vaishnavi.
Sir, I am here.
Okay, now you can present.
Sir, I am using Pavitra's laptop. I have some technical issues with my laptop. So
Shall I call the next?
No, sir.
No.
I'm presenting now. Sir, I am not able to share the screen. I'm looking on it, sir.
So you take your own
No.
time, and I will call the next speaker, and you can present after that.
Okay, sir. Okay, sir.
So now over to.
Hello.
Seven. Okay. Are you okay, Pavitra? Are you okay, Vaishnavi? No. Now we go to abstract number 71. Restricted shuffle of Parikh word representable graphs.
Hello, sir.
And after this, Vaishnavi will present. After this. So I call Nobin Thomas.
Yeah, sir. Am I audible, sir?
Okay, you are audible.
Is the screen visible?
Yes. So you have 13 minutes for presentation and 2 minutes for discussion.
Okay, sir. Good afternoon, all. Myself, I am Nobin Thomas. Dr. Lisa Matthew is my supervisor, and our topic of presentation is restricted shuffle of Parikh where representable graphs. It's a joint work with Somnath Behra and KG Subramanian sir. This is an outline of the presentation. Where representable graph is young, promising research area which relates graph structures with words which are finite sequence of symbols. In 2016, Somnath Behra and Kalpana Mahalingam introduced the idea of Parikh where representable graph by linking the concept of subwords of a word and graphs. Here we study the properties of Parikh where representable graphs.
One second, Nobin, your video is not visible. See, will you switch on your video?
Okay, sir. Okay, sir, sorry.
Okay.
Here we study the properties of Parikh where representable graphs corresponding to the restricted shuffle of two words over an ordered alphabet. An ordered alphabet sigma x is a finite non-empty set of symbols with an ordering on the symbols. For example, the binary ordered alphabet a less than b is the alphabet ab with an ordering a less than b. We use the notation sigma 2 for denoting binary ordered alphabet AB and sigma 3 for denoting ternary ordered alphabet ABC. A word or a string is a finite or infinite sequence of symbols chosen from an alphabet. The length of a finite word is the number of symbols in the sequence. For example, consider the word W equal to AB, ABC, which is a finite word of length having finite word of length 5. An empty word is a word having length 0 and is denoted by lambda. The set of all non-empty words over an ordered alphabet sigma x is denoted by sigma s plus, and set of all words over an ordered alphabet sigma s is denoted by sigma x star, which is known as the clean closure. A subword or a scattered subword of a word W is a subsequence of W. For example, consider W equal to AC AB square AQB C square AB, then BA BCA is a subword of W. The number of occurrence of the word U as a subword of W is denoted by this symbol. For example, consider the word AB A square BA. In this word, number of AB is 4, namely, the mirror image of a word over sigma S star is denoted by Mi of W and is defined as mirror image of W equal to lambda if W is an empty word, and an minus 1, etc. A to A1 if W equal to A1, A2, etc. An. For example, consider W equal to ABCAB, then its mirror image is BACDA. A word over sigma x is said to be a fair word if it contains for each pair of distinct symbols AI, AJ, equal number of distinct occurrence of the subword AI, AJ and AJ, AI in W. For example, consider the word W equal to ABBA, which is a fair word since number of ABs and number of BCs are same and equal to 2. A core word, suppose W is a word over sigma 2 star. The core of W is the unique word W naught of W with the smallest possible length such that W belongs to B star, W naught, A star. A word W is a core word. If and only if core of W is W itself. A non-empty binary word is core word if and only if it starts with A and ends with a B. The support of a word is denoted by sub W is the set of all A belongs to sigma x such that number of A's in W is non-zero. For example, W equal to BCCBC, which is a ternary word, but its support is BC because the alphabet A is absent here. A word D of W equal to Y1, Y2, etc. Yn over sigma 2 is said to be the dual of the word W equal to X1, X2, etc. Xn if Ya equal to B if Xn minus I plus 1 equal to A and A if Xn minus I plus 1 equal to B. That is, first if a word is a dual word, first of all take the mirror image and then replace A by B and the vice versa. For example, AB, A square B and AB square AB are duals of each other. Similarly, we can define the dual of a ternary word. Here we replace A by C and C by A and there is no change for the alphabet B. For example, W equal to A square BC ABC, then its dual is ABCA BCC. A self-dual word is a word whose dual is the word itself. For example, AB square ACB is a self-dual word over sigma 2 and ABC BABC is a self-dual word over sigma 3. Now, the restricted shuffle or a shuffle operator of two words of equal length over an ordered alphabet sigma x, where U is U1, U2, etc. UL and V equal to V1, V2, etc. VL, denoted by a shuffle of UV and is defined as U1, V1, U2, V2, etc. UL, VL. For example, consider the word U equal to AB, ABC and V equal to ABC, AB. Then its shuffle is A square, B square, ACB, ACB. Now, the definition of Parik word representable graph. For each word W equal to W1, W2, etc. Wn of length n over sigma x, we define a simple graph G of W with n labeled vertices 1, 2, 3, etc. n representing the positions of the letters Wi in W such that corresponding to each occurrence of the subword AI, AI plus 1 in W, there is an edge between the corresponding positions. We say that the word W represents the graph G of W. A graph is Parik representable if there exists a word W that represents. For a binary word, G of W contains an edge corresponding to each subword AB of W. Similarly, for a ternary word, G of W contains an edge corresponding to each subword AB or BC of W. Let us have an example. First of all, consider the word A cube, B cube. Here the vertices 1, 2, 3 represents the positions of first 3 A's and 4, 5, 6 represents the positions of B's, and we have a subword corresponding to the positions 1 and 4. Therefore, we have an edge, and we have a subword AB corresponding to the positions 1 and 5. Therefore, we have an edge between 1 and 5, and so on. The second graph is the graph corresponding to the word AB square ABA, which is a disconnected graph because it ends with a A. This is a graph of over ternary alphabet, the graph corresponding to the word A square, B square, ACB, ACB. Now, these are some properties. Every Parik word representable graph is bipartite. A Parik word representable graph corresponding to a word over sigma 2 is connected if and only if it's a core word. A Parikh where representable connected graph corresponding to a word over sigma 3 is regular if and only if it is KNN and it is representable by a word of the form a raised to p, b raised to n, c raised to n minus p, and is a semi-regular if and only if it is kmn and is represented by either of the form a raised to p, b raised to n, c raised to m minus p, or a raised to p, b raised to m, c raised to n minus p. Now, these are our main results. Shuffle of u and mirror image of u is always a fair word for a word over binary alphabet. The shuffle of uv is self-dual if and only if v is dual of u, where u is a binary or ternary word. For words, for binary words u and v, dual of shuffle of uv is same as shuffle of dual of v and dual of u. Now we define the graph corresponding to the shuffle. Suppose g of u and g of b, Parikh were representable graph corresponding to the words u equal to u1, u2, etc. ul, and v equal to v1, v2, etc. vl, having l vertices. Then the graph corresponding to shuffle of uv consists of the vertex at v, which are the vertices vertices 1, 2, 3, etc. 12, and edges e equal to union k equal to 1 to 8 ek. The sets ek are given below. Here E1 and E2 are the edge set for g of u, and E3 and E4 are the edge set corresponding to the graph g of v. This is an example for a graph corresponding to the shuffle of the words AB, ABC and ABC, AB. Now we have a result about connectivity. When u and v are two binary ordered alphabet having same length with at least one alphabet, then such that g of u and g of v are connected, then their shuffle is also connected. The converse of the above theorem is not true. Consider the binary words u equal to AA and v equal to BB. Then its shuffle is AB, and which is a core word. Therefore, the corresponding graph is connected, but neither u and nor v is connected because u and v are not a core word. Now we extend this theorem to ordered alphabet over sigma 3. If suppose u and v are ternary ordered alphabet and support of u equal to support of v equal to sigma 3, such that g of u and g of v are connected, then its shuffle is also connected. Here also the converse is not true. For example, consider u equal to ACB and v equal to BAC, then its shuffle ABC is connected, but g of u and g of v are not connected. These are some conditions.
You have only 1 more minute.
Here we found some conditions for regularity, and similarly we found conditions for semi-regularity on ordered binary or ternary alphabets. And here for any two words, to any two binary words, shuffle of uv is Euler if and only if u equal to v for some core word u, and the restricted shuffle of two binary isomorphic Parikh where representable graph is either Eulerian or self-dual. These are our main references. Thank you.
Now questions? Questions from participants? Questions? So now then I have only one question.
Okay, sir.
Your results are very nice.
Okay, thank you, sir.
Can we extend this to a ternary, or see you have used in your discussion, you have used two symbols, binary words, or some at some place you mentioned ternary words.
Okay, sir.
Can we extend this to an n symbols?
Surely, sir.
So that if you do that, all these then will become particular cases.
Okay, sir. Yeah.
So I suggest that you can do that. if it is
case.
comfortable to do.
Okay,
I don't know. I don't know whether it is.
Okay, sometimes we didn't get a good result. Here also, here we have this result about that fairness. It is only
Okay,
true
okay,
for
okay.
binary
Yeah,
case.
oh,
It is
okay,
not
binary
true for
cases.
ternary case. Okay, sir.
Yes, yes, yes. So excluding this, so you
Okay,
can
yeah.
keep this as two particular cases.
Okay,
And
sir. Yeah,
other
okay.
aspect can be investigated for 10 symbol words if
Okay,
possible.
sir, surely. Okay.
Okay. So as there are no other questions, let us thank the speaker, Nobin Thomas, for his nice presentation.
Thank you, sir. Thank you.
So now over to Vaishnavi. Vaishnavi, are you okay?
Yes, sir.
Okay. So over to Vaishnavi for, and she speaks on fold thickness of graphs. Okay, over to Vaishnavi.
So good afternoon all. First of all, I would like to thank the organizers of ICNTDM for giving us an opportunity to present our paper. My topic is fold thickness of graph. I have done this work under the guidance of Dr. Reggie. So I am moving on to my presentation. This is the outline of my presentation. The concept of fold thickness was first defined by F.J.H. Campina and S.B. Gervasio in 2020. Next, let me define what fold thickness is. Definition. Let G be a graph that is not isomorphic to a complete graph. The graph G dash obtained from G by identifying two non-adjacent vertices in G having at least one common neighbor and reducing the resulting multiple edges to single edges is called one fold of G. Next I define what a K-folding is. A sequence of graphs G equal to G0, G1, G2, etc. Gk, where Gi plus 1 is a one-fold of Gi, for I equal to 0, 1, 2, etc. K minus 1 is called a K-folding of G0. A graph G is said to have a uniform K-folding if there is a K-folding in which all graphs in the sequence are singular or all of them are non-singular. Here, a graph is said to be singular if its adjacency matrix singular, and non-singular means if its adjacency matrix is non-singular. The largest such K, the largest integer K for which there exists a uniform K folding of G is called fold thickness of G, and this fold thickness is denoted by fold, bold letters fold of G. Next, I state some important results that are already proved that will be useful in our discussion. Let G be a simple connected graph. The smallest complete graph that G folds into is the complete graph with order chi of G. Here chi of G represents the vertex chromatic number of G. Next theorem states that if there is a graph and if there are two vertices in that graph having same neighbor set, then that graph will be singular. Next theorem states the determinant of adjacency matrix of complete graph. Next is an important theorem that we use in most of our discussions. Let x and y be vertices in a graph G such that n of x is contained in n of y. If G dash is the graph obtained from G by deleting all the edges of the form yz, where z is a neighbor of x, then determinant of adjacency matrix of G will be equal to determinant of adjacency matrix of G dash. This is also an important theorem. This theorem gives the upper bound for the fold thickness of a general connected graph. For any connected graph G of order n, fold thickness of G is less than or equal to n minus chromatic number of G if G is non-singular, and n minus chromatic number of G minus 1 if G is singular. From this theorem, we can observe that if there exists an n minus chromatic number of G uniform folding and fold thickness is less than or equal to n minus chromatic number of G, we can conclude that fold thickness is equal to n minus chromatic number of G if it is non-singular, and if it is singular, we can conclude that it is equal to n minus chromatic number of G minus 1. Next theorem gives the determinant of adjacency matrix of cycle graph. Now I move on to our main results. First, we will discuss the fold thickness of lollipop graph. The lollipop graph, the ML lollipop graph is the graph obtained by joining a complete graph Km to a path graph with a bridge. This graph is denoted by LMN. I will show an example. This is the lollipop graph L45. First, we state a lemma. For m greater than or equal to 3 and n greater than or equal to 1, determinant of adjacency matrix of lollipop graph LMN is equal to this if n is even and this if n is odd. From this lemma, we can conclude that lollipop graph is always non-singular. This is the main result. For m greater than or equal to 3 and n greater than or equal to 1, the fold thickness of lollipop graph LMN is given by fold thickness is equal to n. Fold thickness of lollipop graph is equal to n. This is the outline of the proof. First, we can observe that fold thickness is less than or equal to n. Then we find an n uniform folding. From these both, we can conclude that fold thickness is equal to n. This is the folding process of lollipop graph. An example is shown here, L45.
So first, sorry, can you show the just the previous slide folding of?
Yes, sir. Yes, sir.
So which two vertices you fold?
This is our first graph.
Vertices.
Yes, this is our first graph. Path vertices starting from pendant vertex. Okay.
Okay.
Next is hem graph. Hem graph is the graph obtained from an wheel graph by adjoining a pendant edge at each vertex of the cycle. Also, we can observe that determinant of hem graph, adjacency matrix of hem graph is always 0 for n greater than or equal to 3. So we can conclude that hem graphs are all singular graphs. This is the main result for hem graph. If n greater than or equal to 3, fold thickness of hem graph is equal to 2n minus 4 if n is even, 0 if n equal to 3, and 2n minus 5 if n is odd and n not equal to 3. This is the outline of the proof. Next, I move on to web graph. This is the special graph, the graph Cartesian product Cn cross P2 with a pendant edge adjoined at each vertex of the outer cycle. This graph is usually called web graph and it is denoted by Wn. This is an example of W8. Here the outer in each vertex of the outer cycle, a pendant vertex is adjoined. Sorry, a P2 is adjoined. Next lemma, this gives the determinant of the adjacency matrix of web graph. Determinant of adjacency matrix of web graph is 0 if n congruent to 0 mod 4, minus 1 power n into 2 if n is odd, minus 1 power n plus 1 into 4 if n congruent to 2 mod 4. From this, we can conclude that web graph is singular if and only if n is congruent to 0 mod 4. This is the main result for web graph. Fold thickness of web graph is equal to 0 if n is congruent to 2 mod 4 and 3n minus 3 otherwise. This is the proof outline. Next is an important classes of graphs. It is rooted product of graphs. First, I define what a rooted graph is. A rooted graph is a graph in which one vertex is labeled in a special way so as to distinguish it from other vertices. The special vertex is called root vertex of the graph. Let G be a label graph on n vertices and H be a sequence of n rooted graphs h1, h2, etc. hn. The rooted product graph G of H is the graph obtained by identifying the root of Hi with the ith vertex of G. Here, we consider only the particular case of rooted product graph where H consists of n isomorphic copies of rooted graph H with a root vertex B. Here in the definition, this H1, H2, etc., Hn may be different graphs. But in this section, in our discussion, we are considering only a special clause with H1, H2, etc., Hn are all same rooted graph. Thus, the rooted product of a graph G and a rooted graph H is defined as follows. Take cardinality of V of G copies of H, and for every vertex Vi of G, identify Vi with the root vertex V of the ith copy of H. It is denoted by G rooted product H with respect to V. This V denote the root vertex of H. This is an example showing the rooted product of complete graph K5 and rooted graph P3. Rooted path graph P3. Here root vertex is taken as a pendant vertex of the path. So this is the resultant graph. For each vertex of K5, this root vertex is adjoined, identified with it. So this is the lemma giving the determinant of adjacency matrix of rooted product of complete graph and path graph. This is the determinant if n is even and this if n is odd. From this lemma, we can conclude that rooted product of complete graph and path graph are all non-singular graphs. This is the main theorem. For m greater than or equal to 3 and n greater than or equal to 2, fold thickness of rooted product of complete graph Km and Pn is equal to 0 if n is even and m into n minus 1 if n is odd. This is the proof. These are the references. That's all. Thank you.
Okay. Now it is time for discussion. Questions? Questions from audience?
You talk about rooted, rooted at a vertex.
Yes.
I just want to go to that example where you take the pendant vertex as the root and join it with the Km and K, something like that.
Yes. Yes, ma'am.
You go to that slide. Okay, now here you have a complete graph. You have rooted with P3 at vertex V, which is a pendant vertex. Okay. Now find out its whatever further you singularity and non-singularity, you find out. Now my question is, your Km given graph remains the same. When you root it, how many times I can root? There are different ways. I can root it 3 ways. 2 ways, at 2 verses, they will be same graph, isomorphic.
Yes.
Okay.
2 pendant vertices and
vertex. Okay. When I rooted the central vertex,
it will be different graph.
The different graph.
Yes.
Now my question is, once you root it, different vertex, of course, you should not get isomorphic. Will you, from here, you can say something about that 2 non-isomorphic graphs obtained by rooting this one will be singular or non-singular?
Ma'am, I'm working on it. I'm not aware of it. Here, I only consider the rooted
because
with root vertex, pendant vertex.
This is rooted. You can always match it with your corona operation, because you are putting a corona only with you're taking a copy of the graph and putting the corona only with the root of that graph.
Yes, yes.
Okay. Secondly, when you talk about this problem, if you have G, you talk about folding and all of that. Have you thought with the connection with this line graph, total graph, and all other things?
I didn't understand, ma'am.
See, here you are determinant of
determinant of S lemma. That lemma.
That's with this operation with Pn, no?
Here also V is taken as the pendant vertex. I'm only considering the root vertex as pendant vertex. In this case also.
I want to know. See, you take a determine. You think about a star, okay, and find out whether it is what you call it singular or non-singular. Now, when you take the line graph of that star, what you can say about the line graph, whether it's singular or not singular? That
Ma'am,
is
I will look upon it.
what?
Ma'am, I will look on it, ma'am. I will check it.
Because you look at the same operation, what is the operation you are taking, singular, non-singular, as you are defining, what how it will change when you have some operation on that graph.
Ma'am, can you repeat once again, ma'am?
You take any graph, G,
Okay.
and find out whether it is it is singular or non-singular, okay? Then take its line graph and see the same operation with respect to line graph. Where they are related, if G has that operation, whether its line graph will have that property.
Line graph, whether the line graph preserves or not, that is that your question, ma'am? That I don't know, ma'am. I will look on it.
For which this property is preserved under the line operation.
That I don't know, ma'am. I will look on it.
Okay, thank you.
Okay, any further questions? Pavitra?
Sir, Vaishnavi.
Vaishnavi, okay. What is the technique you use to find the determinant of this adjacency matrix?
Sir, I will show. In the preliminary, I stated a theorem. This theorem is mainly applied. Sir, I will show. This is the theorem mainly used to find the determinant. Sir.
Okay. Okay. Also, you go to slide 10.
Slide 10. Yes.
Okay. See how you find the folding of L45 here. So first
this is the first graph L45.
Okay. Then you consider.
Then I consider pendant vertex and fold it with the eligible vertex. This vertex and this vertex is folded. This vertex and alternating.
So the alternating vertices are
folded.
Okay.
Then I get this graph. Then continue the process to remaining graphs until the complete graph is obtained.
So given any graph, is this process is a convergent process?
Sir?
So given any graph G, can you ensure that this process is a convergent process? So that this will end with some complete graph?
Yes, sir. Any incomplete graph can be folded.
Okay, any incomplete graph can be folded, and after a finite stage, you will reach at a complete graph.
Yes.
So what happens if the graph has two pendant vertices which are not adjacent but have no common neighbors?
Two pendant vertices. Two
pendant vertices which are non-adjacent but have no common neighbors.
Sir, so it will be K2, is it, sir?
No. So for example, you consider a graph, the self-complementary graph on 5 vertices.
Sir, can you repeat it, sir?
So you consider any graph G. So suppose G has two pendant vertices, say U and B, which are not adjacent. And unfortunately, they have no common neighbors.
Okay, there will be other vertices having common neighbor with that pendant vertex. So we can identify with that vertex.
Are you sure always? So that is a conditional statement.
The definition is yes, sir. Definition is if there exist two non-adjacent vertices having at least one common neighbor, we can fold.
Okay. So my question seems significant. We cannot fold all graphs.
Okay. Yes,
so this process may not be convergent.
That is condition. If there exist such vertices, we can fold.
Okay. Okay. So then I think you can go for a characterization of something like that.
Okay, sir.
Okay. If there are no other questions, we can conclude this. And congratulations to Vaishnavi for the nice presentation. So now, abstract number 75. Domination number of a complement of signed graph. Jayalakshmi, Purupaswamy, and Arokiraj. Who is presenting? Jayalakshmi?
Jayalakshmi, sir.
Jayalakshmi. Okay. Okay, now you can present.
Good evening to one and all present here. Sir, can you see my slides, sir?
I can't see as of now.
Sir, I have shared my screen. Can you see that, sir? Sir?
I think I have some, you continue.
Okay, sir. Okay. I am Jayalakshmi. First of all, I thank you, the organizer gave opportunity to present the paper.
I cannot see the her presentation.
Okay, I too cannot see.
Okay.
See the screen of Pavitra got
Right,
stuck. Still it says you are viewing Pavitra's screen. I don't know what happens. So I thought that it was a technical error at my end.
Only I am able to see Professor Indula yourself on the full
Yeah,
screen.
yes.
Sir, can you see my slides, sir?
No.
You cannot start screen share while other folks. Sir, I have one message, sir. You cannot start screen share while the other participants are in. Okay.
That is why I told you that you can continue, but I can't see. And also Professor Bhakti Acharya also says that she too cannot see.
Yes.
Wait, sir. I will share. Okay. I have technical problem. Wait, sir.
The PPTs are not there. It is not.
I have PPT, sir, but I cannot share it. Please wait, ma'am.
If somebody is already the previous person is sharing, and the previous person has to quit.
Pavitra, you have to quit from the presentation. Vaishnavi?
I think she has not quit. That's what we are.
Yeah, that is what is happening. Vaishnavi, Pavitra? Raji sir, are you here, sir?
I asked the person who is going to first or let her quit the meeting and then join.
Okay, madam. Okay, madam.
Participant wants to let her.
My Jayalakshmi, madam. My name is
Jayalakshmi. You leave the meeting and then join it.
Okay, madam. Okay, madam.
That is the only way we can see whether there is a technical problem.
Okay, madam.
Raji sir, are you here?
Screen is being shared by two people. Therefore, the problem because coming Zoom is sharing your screen. So these two people are. New sharing is not taking place. Pavitra,
Vaishnavi, are you there?
They have to quit. They are not able to hear. Maybe they have left the meeting.
Yeah, maybe.
Yes, sir.
Vaishnavi, you quit your presentation, please.
You stop sharing?
Sir, current പോയതാണ് sir. ഇപ്പോ ശരിയാക്കാം sir.
Okay.
That's what. She has not. The screen is still being shared. Organizers are not there to take care.
Yeah, Vaishnavi told that she has a power failure and she will make this work as early as possible.
Announced.
Okay, okay. Jayalakshmi?
Yes, sir.
Okay, you start presentation. I
Okay.
think now it works.
Okay, thank you. Good evening, sir. Can you see
Yes,
my?
yes, yes,
Okay.
yes.
Thank you, sir. Thank you very much. I am Jayalakshmi, Department of Mathematics, Kalasalingham Academy of Research and Education. It is in collaboration work. My topic is domination number of a complement of signed graphs. This is an overview of my presentation. First one is introduction of signed graph. Next one is definition of domination in signed graph. Next one is definition of complement of signed graph and the following results and reference. This is the introduction. First one, the definition of the signed graph. What is the signed graph? The signed graph is an order for capital sigma equal to g comma small sigma, where g is an underlying graph of capital sigma and small sigma is a function from edge set of sigma to plus comma minus is a function. This function is called as a signature or signing function. Earlier that Dr. B.D. Acharya introduced the concept of domination in signed graph. After that, Arumugham introduced the concept of domination in signed graph in another way. This is the definition of domination in signed graph. So first, let G be a signed graph. That S subset of V of sigma. Then S is said to be a dominating set if the cardinality of n plus of V intersection S, which is greater than the cardinality of n minus of V intersection S for all V in V minus S. So for all vertices in V minus S, satisfy the condition the cardinality of n plus of V intersection n plus of V intersection S, which is greater than cardinality of n minus of V intersection S. That means the positive neighbor of V intersection S, which is strictly greater than the negative neighbor of V intersection S. So whatever the conditions, that for all the vertices in V minus satisfy the condition, the set is called the dominating set. So the domination number of sigma is denoted by gamma S of sigma and is the minimum cardinality of a dominating set of sigma. So also any dominating set of sigma which cardinality equal to gamma S, which is called the gamma set of sigma. Clearly, every dominating set of sigma is also a dominating set of the underlying graph G, and hence it follows that gamma of G, which is less than or equal to gamma S of sigma. This is an example. This graph is called the signed graph. Signed graph means the dotted lines are called the positive edge and the dashed lines are called the negative edge. So this is a signed graph. From this signed graph, we can find the dominating set. So from the signed graph, see that V2 is a one point, that is a V2 is a vertex. Other vertex V1, V3, V4 and V5. So V1, the positive neighbor of V1. So V1 intersection V2 equal to 1 and the negative neighbor of V1 equal to intersection V2 equal to empty. Similarly, V3 also the positive neighbor intersection V2 is 1 and negative neighbor intersection V2 is 0. And similarly V4 and V5. So the V2 is the only set, the other set V1, V3, V4, V5 satisfy the condition. So the V2 set is a dominating set and also it is a minimum dominating set. So the gamma S of sigma which is less than gamma S of sigma equal to 1. Next we are going to see about the complement of the signed graph. So from the take the signed graph sigma, the complement of the first kind of sigma is denoted by sigma alpha complement and is defined as follows. The sigma alpha complement has the same vertex set as sigma and the edge set E dash of sigma alpha complement that is equal to set of all UV such that UV is a positive edge of sigma and UV does not belong to E of sigma and sigma dash, that is a small sigma dash of sigma alpha complement from 2 E dash 2 plus comma minus is defined as follows. Sigma dash of UV equal to minus when sigma of UV equal to plus. If UV does not belong to E of sigma, then sigma dash of UV equal to plus. That means if UV is a negative edge of sigma, then U and V are not adjacent in sigma alpha complement. And also, if U and V are not adjacent in sigma, then becomes UV is a positive edge of sigma alpha complement. This is the definition of the complement of signed graphs. In this paper, we obtained some bounds for the domination number of sigma alpha complement, and further we have find the Nada's garden type results are obtained. This is the example. This is the first one is a signed graph. Signed graph sigma is a signed graph. The sigma alpha complement is a complement of sigma. See that V1, V2 is adjacent in sigma. That is a positive edge, and V1 and V2 is a negative edge in sigma alpha complement. And also V1, V4 are non-adjacent in sigma. That becomes a positive edge in sigma alpha complement. And also see that V1, V4 is non-adjacent in sigma. That becomes a positive edge in sigma alpha complement. This is the definition for the complement of signed graph. These are the theorems for that. Let sigma be a signed graph and sigma. Ma'am, let sigma be a yes, sir.
Teleshmi, you can switch on the video also.
Okay. Okay, sir.
Okay.
First theorem is that sigma be a signed graph and sigma alpha complement be the complement of sigma. Then gamma is a sigma alpha complement which is greater than or equal to n divided by 1 plus delta plus alpha. That means delta plus means a maximum positive degree of sigma alpha complement, that is denoted by del plus alpha. And next theorem is sigma and sigma alpha complement have no isolated vertices. Then gamma is a sigma plus gamma is a sigma alpha complement which is greater than or equal to n times of n minus small delta plus capital del plus 1 divided by n minus delta into del plus 1. Here delta means minimum degree of sigma, and del plus means maximum positive degree of del plus. So furthermore, the lower bound is sought for signed cycle graph of order n with negative edge only. Next theorem is if signed graph has an isolated vertex, then gamma is a sigma alpha complement equal to 1. Next theorem is if sigma be a signed complete graph on n vertices, then gamma is a sigma alpha complement is equal to n. Next theorem is if both sigma and sigma alpha complement have no isolated vertices, then 4 less than or equal to gamma s of sigma plus gamma s of sigma alpha complement which is less than or equal to 2n. The lower bounds are attained on the sigma signed graph which is isomorphic to the cycle graph on 4 vertices and path on 4 vertices and K1, n. For every vertex V in V of sigma, degree plus of V equal to 1. And also the upper bounds are attained on the signed graph on complete graph on n vertices, such that every vertex in V of sigma with the condition is smallest degree del minus of Kn which is greater than or equal to lower part of n divided by 2. Next theorem is let sigma be a signed cycle graph on n vertices, signed cycle graph on n vertices. Then gamma is a sigma alpha complement which is less than or equal to 4, and the bound is sharp on signed cycle graph on n vertices, that is n equal to 4 with exactly 1 negative edge. Another theorem is sigma be a signed tree on n vertices. Then gamma is a sigma alpha complement which is less than or equal to 3, and the bound is sharp on signed path graph sigma of order n with exactly 1 negative pendant edge. Next theorem is theorem on cycle wheel graph. So let sigma be a signed graph whose underlying graph is Wn with n greater than or equal to 3. Then gamma is a sigma alpha complement which is less than or equal to 6. Also find the lower bound and upper bound for next theorem. For any signed graph sigma without isolated vertices, the lower part is 2, that is a 2 less than or equal to gamma s of sigma alpha complement which is less than or equal to n. So we have get the equality holds on lower bound on signed graph whose underlying graph is mk2, and equality holds for the upper bound on signed graph whose underlying graph is complete graph on n vertices. Next, another upper bound is if del plus of sigma and small del plus of sigma is denoted by the maximum and minimum positive degree among the vertices of signed graph, then gamma s of sigma alpha complement which is less than or equal to capital del plus of sigma and plus small del plus of sigma plus 2. Next theorem is If there are no isolated vertices in sigma and sigma alpha complement, then 4 less than or equal to gamma s of sigma plus gamma s of sigma alpha complement, which is less than or equal to 2n. The lower bound is attained on a signed star graph with del plus of sigma equal to n minus 1, and upper bound is attained on a signed graph on n vertices with condition del minus of sigma, which is greater than lower part of n by 2. This is a reference, sir. Thank you, sir. So any questions?
Now it is time for questions.
I want to ask, I want to clarify, I want to know one thing.
Okay, ma'am.
Okay. Since sign graph, we have 2 type of colors and then many ways to define the definitions. Okay.
Okay, ma'am.
I take a graph.
Okay.
You take its complement.
Okay,
we will define. Then take the complement of a complement.
Okay, ma'am.
Come back to the given graph.
Yes,
now, under your definition,
yes, ma'am.
if I have a sign graph,
Yes,
I
ma'am.
take the complement and you take it.
Okay, ma'am.
So we get another sign graph.
Mm.
And take the complement of that complement of the sign graph under your definition. Will you come back to the original sign graph?
I can't understand, ma'am. This is the example of signed graph. He told that the complement of another complement of sigma alpha is equal to sigma.
What happens? You have taken a sigma, then you have
Yes,
taken a
complement.
Okay. Now you take the complement of this
complement graph.
Yeah, under your definition.
Yes, sir. We can get the original graph.
Sign graph.
Yes, sir. Yes, ma'am. This is one type of complement definition, ma'am. We can define another way. What we way for positive edge become
under this definition. What you positive, negative edges, whatever. You should when we generalize results to anything, we can have 100 types of complements with respect to sign graphs. But people who are working in sign graph, their main aim is, are we able to get a definition of a complement of a sign graph? And when we take the complement of the complement, I should be back to the original sign graph.
Yes, ma'am. Original sign graph.
Because then we will not be missing much. Okay.
Okay.
Have the, but in this one, it is under new definition. You can create a theory and other things, and how far that theory will be taken up, I don't have any idea, because we are stuck up in a complement sign graph. But recently, in one of our papers with Professor Joseph, we have taken, we have given the complement of a sign graph under some property. Okay. And then maintaining that property, we take the complement of the complement, we go back to the original sign.
Original sign graph.
But further study has yet to be taken up because it is still at the raw material. We have.
Okay, ma'am. I will try to the complement of the complement graph. Okay, ma'am.
Because I want to stick to the rules of the graphs. Complement of the complement of a sign graph, we should come back to the original sign
graph.
Because it's self-complementary and all other things.
Yes,
but in this definition, we will not be able to talk about self-complementary sign.
Yes, ma'am. We are not talking about self-complementary.
Yeah, we will not be able to. I don't think here under this definition, you come back to the original sign.
Yes, ma'am.
Try to find a definition under this one only, then you may be able to you may be able to do that one. Okay.
Okay, ma'am.
Okay, then you may be able to do it. But if you want to see our definition, our paper is already on archives by Professor Jaslavsky. Where we give the new definition of a complement under some
conditions.
Operation. Maintain that operation when we take the complement of the complement
graph with the original graph. Original graph. Yes, ma'am. I will try that.
And we have posed a lot of problems with respect to that also.
Okay. Thank you. Thank you for giving valuable.
Thank you very much.
Thank you.
Okay. Any other questions?
Jayalakshmi, can you send me this paper?
Yes, what do you, ma'am?
Is it published, this paper?
No, ma'am. It is not published. It is a conference proceeding on this paper.
Then you give me just the definitions.
Which one, ma'am?
You just give me, because I'm not able to write it. I just want the definitions, how you define the.
This one is my definition, ma'am. I have defined the definition.
I will not be able to write it. I will not be able to write it. No.
Okay, okay.
So you can, Jayalakshmi, you can give this definition to Mukti Acharya by through email.
Definition of domination sign graphs, new definition. And then you are this complement definition.
Okay,
I want
okay.
only definition. I don't need any other one. Another.
Okay, I will follow you. I will follow.
You can have my mail. No.
I don't know my mail. I don't have your mail.
You all must be having my mail.
I will search and I will send you, ma'am. I will call you, ma'am. Okay, ma'am.
Surely you can call me.
Okay, sorry. Thank you, ma'am. Thank you very much, ma'am.
Okay, so I hope that there are no other questions. And also, I had the same question. Professor Mukti Acharya already asked this question, so I have no questions for us for time being.
Okay, sir.
So we congratulate Jayalakshmi for the
Thank you very
presentation.
much. Okay, sir. Thank you very much. Thank you.
Okay, over to next speaker. Abstract number 83. Arun Anil.
Jayalakshmi,
Okay, wait, ma'am.
He speaks on comparability graphs, which are cover comparability graphs. Jayalakshmi, please quit. Okay. Then over to Arun Anil.
Okay, thank you, sir. Sir, is it visible?
Yeah, is it visible? Yeah, yes, visible. But your audio is very low. So
Audio
that
sir, can you hear me? Hello?
yeah, it is little bit. You can make it, if it possible, you can make it little bit louder.
Hello, sir, can you hear me?
Yeah,
no?
okay.
No, is it visible? Is it audible?
It is not comfortably audible.
Oh, sorry, sir. Just a second. Sir, now is it audible?
Ah, yes, yes, yes.
Okay. Good afternoon to all. First of all, I introduce myself. My name is Arun, Research Scholar, Department of Future Studies, University of Kerala. I am doing research under the guidance of Dr. Manoj Changat, Professor, Department of Future Studies. Coming to the presentation, the title of my presentation is Comparability Graphs, which are covering comparability graph. This is the outline of my presentation. Coming to the introduction section, here I give some basic definitions and some basic results. A partially ordered set or pose set PV less than or equal to consists of a non-empty set V and a reflexive antisymmetric transitive relation less than or equal to on V. If U less than or equal to V or V less than or equal to U in a pose set, we say that U and V are comparable. Otherwise, we say that U and V are incomparable. If U less than or equal to V, but U not equal to V, then we write U less than V. If U and V are in V, then V covers U in P. If U less than V and there is no W in V such that U less than W less than V, and this is denoted like this, and V covers U. And coming to the definition of comparability graph and a covering comparability graph, a graph CP is a comparability graph of a poset P if two vertices are adjacent in CP, if and only if they are comparable in P. Similarly, for cover graph of the poset P, if two vertices U and V are adjacent, if and only if either U covers V or V covers U. The complement of comparability graph of a poset P is called incomparability graph. Coming to the definition of covering comparability graph, or shortly CI graph of a poset P is the graph in which the edge set is the union of edge set of corresponding cover graph and corresponding incomparability graph. This graph is introduced in 2008 by Boston and others in the paper covering comparability graph of posets. This is a poset, and corresponding comparability graph is this. This V1, V2, V3, V4, V5, V6 are comparable. So all these elements are mutually adjacent. Similarly, V7, V8, V9, V4, V3, V10. Also, there is also an edge I forgot to draw. Sorry. So these are comparable. So there is an edge, and this is the poset corresponding. This is the comparability graph corresponding the poset P. And also there is an edge here and also here. Okay, and for the poset P, this is the covering comparability graph of this poset. This Hussey diagram gives the cover graph, and we need to make adjacency between the incomparable elements. So V1 is incomparable with these three elements. So we make adjacents. Similarly, V2 is incomparable with all these three elements, so make them adjacent. Similarly for V3, and V6 is incomparable with V10, so we make them adjacent. This is the CI graph corresponding the poset P. I come into the definition of finitely ranked poset. A finitely ranked poset or a graded poset is a poset P V less than or equal to, that is occupied with a rank function rho from V to Z satisfying. Rho has value 0 on all minimal elements of P, and rho preserves covering relation. If B covers A, then rho of B is equal to rho of A plus rho of B is equal to rho of A plus 1. A ranked poset P is said to be complete if for every I, every element of rank I covers all the elements of rank I minus 1. This is some basic results. Let P be a poset, then the CA graph of the poset P is connected. The points of P that are independent in the CA graph of P lies on a common chain, and the CA graph of P contains no induced cycles of length greater than 4. And this is a result which we proved in this paper. A graph G is Ptolemaic CA graph if and only if there exists a completely ranked poset P such that G is isomorphic to GP. That is, the Ptolemaic CA graph is a CA graph of a completely ranked poset. The comparability graph, the recognition complexity of the comparability graph is polynomial time, but the recognition complexity of covering comparability graph is NP complete. Hence, the problem of characterizing well-known subfamilies whose recognition complexity is polynomial time is very interesting. That's why we focus on comparability graph, which are covering comparability graph. Coming to the first section, first main section, poset whose comparability graph are Ptolemaic CA graph. We define a family of poset P as follows. Consider a sequence of disjoint chains. Chains means every elements in the chains are comparable. In poset, every elements are comparable in chains. Okay, L1, L3, we odd number labeled L1, L3, etc. L2D plus 1. Let Li consist of the elements AI1, AI2, etc. AI, Ki, and AI plus 1, 1, etc. AI plus 1, Ki for I is equal to 1, 3, etc. 2D plus 1, and make a cover relation. AI plus 1, Ki plus 1 covers AI, Ki. For where AI, Ki element of Li and AI minus 1, Ki minus 1 from Li minus 2. And in label, this is the figure-wise representation. We know the Ptolemaic CA graph. Ptolemaic graph means it's a distance arbitrary caudal graph. In terms of forbidden subgraph characterization, it is the 3' field caudal graph. So in Ptolemaic CA graph is a CA graph of a completely ranked poset, and this is a CA graph of this form where C1, C2, C3, etc. Clicks, and C1, Ci union Ci plus 1 also click, and there is no other edges. For I is equal to 1 to H minus 1. So for this is a general form of a Ptolemaic CA graph, and the corresponding poset for comparability graph is this. The elements in C1 lies here, and the elements in C2 lies here. This is L1, and the elements in C3 is lies here, elements in C4 is lies here, and continues like that. This is L1, this is L3, this is L5, and continues like this. And C1 is adjacent only to C2, so this only this chain, and C2 is adjacent to both C1 and C3, so here is a chain, and here is also a chain, and continues like this. This is a result. A comparability graph CP of a poset P is a Ptolemaic CA graph if and only if P in the family defined P. And if G is a Ptolemaic CA graph, then G is comparability graph. And in general, every Ptolemaic graph is a comparability graph.
I don't know, 2 more minutes.
Just I skipped this. This is a composition operation. In general, say the composition of CA graph need not be a CA graph. This is an example. We get some definitions. We get some result if G is, it's a composition graph. G is equal to G0, G1, G2, etc. Gn, where G is a CA graph, which are not complete graph for I is equal to 1 to n. Then G is CA graph if and only if G0 is a complete graph. Similarly, G is a Ptolemaic CA graph if and only if G0 is a path on n vertices and G8s are complete graph. This is a result from Coulombic book that G is equal to G0, G1, G2, etc. Gn, where G8s are disjoint graph. Then G is comparability graph if and only if G8 is a comparability graph for I is equal to 0 to n. If G8s, if we get the conditions for G0, G1, G2, etc. Gns such that G is a CA graph, then we can characterize fully characterize the comparability CA graph. Okay, just skip. And this is some subfamilies of covering comparability graph. This is a threshold CA graph. Threshold graph means it's a 2K to C4 P43 graph. And for the CA graph, this is the family of threshold CA graph. That means a click, and this is a click. U and V are adjacent to, both adjacent to clicks, but U and V are not adjacent. This is U, V, W are adjacent to all the elements in the click. V and W are adjacent. U, V, U, W are not adjacent. This is the a graph G is a threshold CA graph if and only it is from this family. And I just skip by split graph. A graph G is by split if its vector set can be partitioned into 3 stable set XY and is set such that Y uni set induce a complete bipartite subgraph. And this is this is the family of bisplit graph, and this is a path graph on 1 vertex, 2, 3, 4, and 5 vertices, and this is the family of bisplit graph. And this and the third family, a split graph in a graph G is vector set VG can be partitioned into sets A and B such that A induces a click and B is an independent set. This is a result from this paper. Let P be a poset, then the CA graph GP of the poset P is split graph if and only if P is a poset isomorphic to one of the poset from the family S1, S2, or S3. This is the family, and this corresponding CA graph is this.
Okay, let me intervene.
Last result, sir.
See, we are running short of time.
Okay. This is the last letter. In general, split graph need not be a comparability graph, but in the case of CA graph, it's a comparability graph. That's all, sir. These are references.
Okay. So any questions? Because there are no questions, let us congratulate Arun Anil for the presentation.
Thank you, sir.
Thank you. You may please quit from. Okay. The next speaker is abstract number 18. Purushottam speaks on pendant domination in grid graphs.
Okay. So screen is visible, sir?
No, not yet.
No?
Yeah. It says it started screen sharing. Okay, now it is visible.
First, I would like to thank the organizer for providing me an opportunity to present my research article in ICNTDM. The title of my research work is Pendant Domination in Grid Graph. So, I am myself Purushottam, Assistant Professor in Department of Mathematics, Maharaj Institute of Technology, Mysuru. Okay, before going to start, my presentation, first we recall the definition of dominating set. So S is a subset of vertex set of any graph G if each vertex in B minus S is adjacent to a vertex in S. The least coordinate of a dominating set in G is called the domination number of G, is usually denoted by gamma of G. This is the definition of dominating set. Then we define that another one definition, pendant dominating set. A dominating set S in G means already S is a dominating set. So S in G is called a pendant dominating set if induced subgraph of S contains at least one vertex of degree 1, at least one pendant vertex. The minimum coordinate of a pendant dominating set is called the pendant domination number. It denoted by gamma P of G. So here I am mentioning the just a cross so Cartesian product of two graphs G1 and G2. If the graph is denoted by G1 into G2, if each G1 and G2 is a path PM and PN, M and N vertices respectively, then we will call PM cross PN is a M cross N grid graph. For notational convenience, we denote PM into PN by PM comma N. So this is the notation of grid graph. Using this definition and denotation, we give the pendant domination number of 2 cross N grid graph at P of 2 comma N if N greater than 2. The first theorem says that for all N greater than 2, pendant domination number of 2 cross N grid graph is greatest integer of 2N by 3. In case if N equal to 2, pendant domination number of, this is the graph. So first to figure 2 represent the grid graph of order 2 cross N. So in this remark, pendant domination number of P of 2 comma 2 is nothing but 2. This is the graph of P of 2 comma 2 cross N. The first is proof of this theorem. Consider 3 cases: case 1, case 2, case 3. In case 1, n congruent to 0 mod 3, case 2, n congruent to 1 mod 3, case 3, n congruent to 2 mod 3. In the first one case, we consider the figure 2 along with A. For case 2, figure 2 along with B. Case 3, figure 2 along with C. In this figure, the vertices enclosed by a circle indicates that particular vertex belongs to the pendant dominating set. So in this section, we give the pendant domination number of 3 graphs and grid graph. So for all n greater than or equal to 4, pendant domination number of P of 3 comma n is nothing but n. In case if n less than 4, what is the pendant domination number means? Pendant domination number of P of 3 comma 1 is 2, 3 comma 2 is 2, P of 3 comma 3 is 3. This is the diagram of grid graph of order 3 cross n. Here also we are considering 4 cases: n congruent to 0 mod 3, 1 mod 3, 2 mod 3. Sorry, here in cases means in this proof of this theorem, consider 4 cases: n congruent to 0 mod 4, 1 mod 4, 3, 2 mod 4, and 3 mod 4. So in this section, we give the pendant domination number of 4 cross n grid graph P of 4 comma n, and n is greater than or equal to 5. So the theorem says that for all n greater than or equal to 5, pendant domination number of P of 4 comma n is nothing but greatest integer of 4n by 3. In case if n less than 5, the pendant domination number is P of 4 comma 1 is 2, P of 4 comma 2 is 3, P of 4 comma 3 is 4, P of 4 comma 4 is 6. This is the picture of means diagram of P of 4 comma 4 cross n, a grid graph of order 4 into n. This is the cases A, B, C. So the vertices enclosed within a circle is the particular vertex belongs to the pendant dominating set. So this is the theorem. In this theorem, for all n greater than or equal to 6, pendant domination number of P of phi comma n, phi into n grid graph is phi n by 3 if n congruent to 0 comma 3 mod 6. In remaining cases, remaining cases, greatest integer of phi n plus 1 divided by 3. So this is the pendant domination number of P of phi cross n. So in case if in the remark for n 1 less than or equal to n less than or equal to 5, pendant domination number of P of phi comma 1 is nothing but greatest integer of phi n by 3. So in the remark, recurrence relation in phi cross n grid graph, gamma pendant domination number of P of phi comma n is nothing but pendant domination number of P of phi comma n minus 6 plus 10 for all n greater than or equal to 12. So this is the figure of P of phi cross n. In this theorem, this is the last theorem in this presentation. For all n greater than or equal to 7, pendant domination number of 6 comma n is equal to 2n. If in case n lies between 1 and 6, pendant domination number of 6 comma n is equal to 2n. The recurrence relation in 6 cross n grid graph is gamma p of 6 comma n is equal to pendant domination number of p6 of n minus 7 plus 14 for all n greater than or equal to 14. This is the figure of p of 6 comma n. This is the cases we are considering the proof of the theorem. These are all the references which are using in our research. Thank you.
Any questions? Any questions?
That is perfect, because I most likely have an answer.
Any questions?
I want to ask, he is taking PMN and giving the values to M.
Back from a search.
1, 2, 3, 4, 5, 6, 7. I want to keep M in general. Does he have result for any M?
No, ma'am, still we are working on that particular cases.
Particular cases. Now, for how long you will go?
Up to n is equal to 10, ma'am.
That is N, M. I'm asking M.
Okay.
I'm asking M.
Okay, ma'am. N value.
Because you are changing M now, M 2, 3, 4, 5, 6. Up to 6, I think you have gone. Naturally, N will also depend, your N value will also depend on N only, on M only.
Yes, ma'am.
Okay? Because after particular, when M goes that one, you have a one number.
Okay.
So my question is, for how long you will go M? How long for M you will go?
N of n is
M,
equal to m.
M
What is the maximum possible value for this M you are going to take?
Ma'am, up to year 7, ma'am.
Do you want to go further?
Ma'am.
Huh?
Ma'am, I'm miss in this
What is this in general? I'm asking.
Okay.
In this you have gone only up to 6, I think, na?
Yes, ma'am.
M is up to 7, something like that.
Ma'am.
I'm seeing your M is equal to 2, M is equal to 3, M is equal to 4,
yes,
and then your N once you go. But when M and N are equal?
I don't know.
Because when M and N, that is they are coming to 3, no? P3, 3 you are coming.
Yeah, ma'am.
P3, 3. But always you put a condition that N should be greater than M, greater is equal to M.
Okay.
And for others, you forcefully calculate, okay?
Okay, ma'am.
I think from your this formula, you should be able to give a general recurrence relation for computing gamma B.
Ma'am.
For M and keep M, this one and do that one. Anyway, thank you.
Thank you, ma'am. Thank you.
Okay, any further questions? If not, as we are running short of time, let us congratulate Purushotthama for this presentation.
Yes, sir. Thank you.
Okay. And the last one of this contributed session is the talk on uniform number of graphs and other graph invariants, abstract number 40, by Elakya Mohan Kumar and Kumar Abhishek. May I know who is going to present?
Hello, yes, sir. I'm here, sir.
Your good name?
Yeah, Ilakya, sir. Ilakya Mohan Kumar.
Okay.
Yes, sir.
So you can start.
Yes, sir. Hello. Sir?
Okay.
Yes, sir.
Yeah, okay. Visible and audible.
Yes, sir. Thank you, sir. My topic is on uniform number of graphs and other graph invariants. And this is a joint work with my guide, Dr. Kumar Abhishek. Then, in this talk, we are going to see some basic terminology and uniform number of a graph, and we are obtaining some results on it, that is interaction with other graph parameters. Then
you can
first
switch on your video as well.
Okay, sir. Sir, when I am switch on the video, it. Hello.
Hello.
Yes, sir.
Okay, if there is a technical difficulty, you can continue as of now.
Okay, sir. Okay, sir. Then first we are going to see what is distance and D2 distance. We are taking a graph with vertex set V and edge set, and its distance is given by the length of the shortest path between the vertices X and Y in G. And its D2 distance is given by the length of the longest path between X and Y in G, and it is denoted by capital D of X, comma Y. And we are seeing some finding the longest path between two vertices of a graph is known to be NP complete, and the problem which involves finding a path of maximum length in a given graph, where the length of a path may either be measured by its number of edges or for weighted graphs by the sum of the weights of its edges is NP hard. And then this is our newly introduced graph parameter, that is for a non-empty subset M contained in vertex set of G, we defined a function fm from M complement to y of x as fm of x is equal to the set of D2 distance between x and y, where y belongs to capital M. It is referred as the assignment, that is fm of x as the D2 pattern of the vertex set X with respect to the set M in the graph G. Then the assignment fm is a constant function. It is referred as the set M as the uniform D2 pattern set of the graph G. And the minimum cardinality of the uniform set of G is referred as the uniform number of a graph G, and it is denoted by tau of G. And the uniform number tau of G for a graph G satisfies the following inequality. That is, for any connected graph G, its uniform number of a graph lies between 1 and n minus 2, and this bounds are short, and the bounds prescribed in this proposition are known to be short, and we are obtaining some of the general results. If G is isomorphic to complete tripartite graph where n greater than or equal to 2, then its uniform number is given by 2. And if for the friendship graph, the uniform number is given by 1. And for a tree of order n greater than or equal to 4, its uniform number is given by 2 if and only if T is isomorphic to bi-star. If G is a barbell graph, that means n barbell graph that is obtained by connecting two copies of a Hamilton connected graph of order n by a bridge, then its uniform number is given by 2. And we see some of the motivating examples which helps us to Hello.
Yes, you are audible.
Yes, sir.
You can continue.
Yes, sir.
Okay.
Okay, sir. And now we will see some of the motivating example which helps us to write our paper. See G1 and G2, and we are taking P5. In figure 1, M1 is equal to set of 1, 2, 3 is a minimum uniform set, and M2 is 1, 4, 5, 6, 7 is a minimal uniform set of a graph G1, which are the uniform sets of distinct cardinality. And then if we are taking in figure 1, for a graph G2, M3 is equal to 1, 2, 3 and M4 is equal to 4, 5, 6. These are the only uniform sets and are of the same cardinality. So here we are seeing that uniform sets for a graph G1 is of distinct cardinality and having the same cardinality. And then in the same figure 1, M5 is equal to 2, 3, 4 is the unique uniform set for the graph P5. So in figure 1, there exists a class of graphs for which the uniform set is unique and therefore having a unique minimum uniform set. Given the preceding discussion, it will be meaningful to characterize the class of graphs having a unique uniform sets. So this is an existence of graph with unique uniform sets. So we are getting some results for which the graphs are having with minimum unique uniform sets. So if we are taking the graph G is isomorphic to K1, n minus 1, where n is greater than or equal to 3 means, then G has a unique minimum uniform set. And if G is isomorphic to complete tripartite graph, where n is greater than or equal to 2 means, then G has a unique minimum uniform set. So next one, if G is isomorphic to NP2 plus K1 is a graph of order n greater than or equal to 2 means, then G has a unique minimum uniform sets. And if we are taking a graph isomorphic to bistar of order n greater than or equal to 4 means, then bistar has a unique minimum uniform sets. So further, it is easy to see that the sets M1 and M2 are minimal dominating sets, and the set D is equal to 2, 3 is the minimum dominating set of G1. It can also be verified that D is equal to 2, 3 is not an uniform set of G1. Hence, the domination number of G1 is not equal to gamma of G1. Also, the sets M3 and M4 are the minimum dominating sets of the graph G2. So, thus, tau of G2 is equal to 3, that is equal to domination number of G2. So, it is follows that from the above discussion that minimum dominating set of a graph need to be an uniform set or vice versa. Further, for the complete graph Kn and the wheel graph Wn or Hamilton, the domination number is known to be unity. So, uniform number and domination number. If G is isomorphic to Kn, that means complete graph, then its uniform number and domination number is equal to 1. And if the graph is isomorphic to the wheel graph, then its domination number and uniform number is equal to 1. If G is isomorphic to Kn, n means, then its domination number and uniform number is equal to 2. And finally, we are having for every m greater than or equal to 1, there exists a graph G such that tau of G is equal to gamma of G, that is domination number of G, that is equal to m. And then we are getting some relationship between uniform number and independence number. For every m greater than or equal to 1, there exists a graph G such that tau of G, that is uniform number of a graph G, is equal to independence number of a graph G, that is equal to beta of G, that is equal to m. So from the corollary, for every m greater than or equal to 1, there exists a graph G such that tau of G is equal to beta of G is equal to gamma of G, that is equal to m. And then the relationship between uniform number and clique number is given by our next result. For every n greater than or equal to 1, there exists a graph G such that tau of G, that is uniform number of a graph G, is equal to clique number, that is omega of G is equal to n. And then we also got the relationship between uniform number, that is tau of G, and chromatic number, that is chi of G. Let G be a graph obtained as the corona product of complete graph H of order n and K1. Then tau of G is equal to chi of G is equal to n. And then these are my references. Thank you.
Any questions? Any questions from participants? Elkia,
Yes, sir.
I have one question.
Yes, sir.
See, what is the relevance of choosing this detour distance between two vertices when there is a usual practical distance available as the usual distance between x and y?
Sir,
we are all...
it's an NP complete problem, sir. Then...
No, I am not asking that.
Okay, sir.
See, when a graph is given and
Yes,
two
sir.
distinct vertices are given, see, we can always have the shortest distance, means the length of the shortest path between x and y.
Yes, sir.
See, once we have a shortest distance between two vertices x and y, then why we go for a path, a longest path joining x and y, and taking that distance as the detour distance? Is there any practical relevance of that?
Yes, sir. It's used in perimeter security problems, sir. Based on that only we are doing this one, sir. Its application is under perimeter security problems, sir. That's why based on that we are taking detour distance, sir.
Okay, anyway, my doubt is still you can reach y from x using the shortest path.
Sir, by using shortest distance, it's already done, sir.
Okay, anyway.
I would like to see the references.
Ma'am?
I would
Show
like
the
to see the references.
References.
Ma'am, I can't hear you.
Just for my knowledge. Because you just skip the reference.
Yes, sir.
Show
Yes,
the
sir.
references.
Yes, sir.
Go slowly because what happens? Go ahead. Okay.
Next page.
I think Kumar Abhishek has worked with this related parameter in the other papers also, is it?
Yes, sir. Yes, ma'am. Yes, ma'am.
But that paper you have not. I'm not finding that paper because that idea you must have got from that only. Okay.
Okay, ma'am. Okay.
Anyway.
Okay, no problem.
Okay, anyway, for the congratulations for the next presentation.
Okay, sir. Thank
so
you,
I think
sir.
this session is over by now, and now over to organizers for further instructions.
On behalf of ICNTDM, I would like to thank Dr. Indulal ji for chairing the session and all the participants for the further presentation. So in the next, in the next session, we have the plenary talk P14 by Professor Neil Koblitz, which will start at Indian time, 5:30 p.m. So the links are published in the official website. I request all the participants to join soon. Thank you all.
Okay, then I'm leaving. Okay.
Yes.